This is lesson 3-2 in your workbook. You'll start on page 172 and work through page 174. Okay, let's start with example number 1. This is on page 172. And as I'm reading, I'm going to start highlighting some important things. You should probably somehow highlight them as well. Whether you underline, circle, highlight, you just need to note the important information. All right, so we have a 10,000 gallon swimming pool, and it's going to be emptied. And it looks like 2,000 gallons are already out of the pool and in the tanker truck. How can you determine how long it will take to pump all of the water into the tanker? So we have this swimming pool right here. It's got 10,000 gallons in it, but we want to empty it into this truck. Notice there's already 2,000 gallons out, and here's something else important. Our rate, 720 gallons per hour. All right, so I think we can probably solve this a couple of different ways. One is with an equation, and one is with a graph. Okay, so option number one, according to your book, is this bar diagram, and that's for my visual learners. They do better when they can see a picture or a diagram. If you look at it, we're going to take our 10,000, that is the total water in the pool, and it's going to be made up of what is being pumped at a rate of 720 gallons per hour, and what has already been put in the truck. So that equation makes sense to me. I have a total of 10,000. It is made up of what is being pumped and what has already been pumped. Your next option is a graph. Now, this probably wouldn't be my go-to, simply because if you look, I'm going to start with 2,000 in the truck. And I have to count by a slope of 720. Up 720 over 1. Up 720 over 1. Repeatedly. And that just seems like it wouldn't be very efficient. But it's possible. So technically, I could take this linear graph, and it's linear simply because it's a nice straight line. And I could write it y equals my rate of change, also known as slope, plus my y-intercept. Now this isn't in your book, but I just want you to look for a second at this equation compared to this equation. The only difference is that we know, according to the book, we know that this is 10,000. Otherwise, it is exactly the same. I'm going to say there's three options here. I probably would skip over the bar diagram and go right to the equation. I would skip over the graph because it's very cumbersome. But it's all about what you are comfortable with. So if you love one of those other options, you should go for it because there are always multiple ways of solving the math problem. Here is the try it at the bottom of page 172. It says, as the pump is pumping water, the amount of water in the pool decreases at a constant rate. Complete the statements below, then graph the function. The amount of water remaining in the pool is blank gallons. The amount of water pumped each hour is blank gallons. The equation is blank. All right, I want you to go ahead and pause me. Come back when you are ready to check your answers. All right, so I know there were 10,000 gallons in the pool, and 2,000 of them happened to be in the tanker. So that leaves, I don't know if I can write this small enough, 8,000 gallons in the pool. And I also know that 720 of them are leaving every hour. So if I take 8,000 minus 720 every hour, I will end up with nothing in the pool. All right, so now it's time to graph it. I know that I'm starting at 8,000 gallons, so that's going to be somewhere up in here. Here's one of the issues that I would have with this graph paper. The 8,000 is a little tricky to find, and you have to count down 720 and over 1, 720 over 1, 720 over 1. That's going to be really difficult to do. So instead, I'm going to estimate my graph. So I know that it's going to go in a downward slope until it hits 0. It's going to look something like that. All right, we are on example number 2 on page 173. And I just want to remind you that this lesson is all about different representations of functions. So far, we have done bar diagrams. We've done equations. We've done graphs. But wait, there's more. You can absolutely use a table as a representation. So example number 2 says, how can you determine whether the relationship between side length and area is a function? And so they created this table. I'm guessing that they just chose some numbers for the side length. So if we happen to have a square, you know you take length times width to get area. 0 times 0 is 0, 1 times 1 is 1, 2 times 2 is 4, and so forth. So they created this lovely table. A table is a representation, but so is a graph. So what they did from there is they created an ordered pair, and they plotted 0, 0. They plotted 1, 1. They plotted 2, 4, and so forth along this line. And when they connected their dots, their graph is a curve. That means it is nonlinear. It is not a straight line. So let's add. We have one more representation to go. We have tables. Now all we're doing is we're making connections between the function and different ways of looking at it. We could use bar diagrams, equations, graphs, tables. The list is endless, I think. All right, example number 3. Can we determine whether each graph represents a function? All right, so here we go. At first, we're going to look at this V-looking graph. And each of these graphs represents a function. So this is a function, and this is a function, because every x value has 1 and only one y value. Now they're not linear, but they are a function. Let me add one thing to this. There's something called a, let me change that. I'm trying to get a pen instead of a highlighter. There's something called a vertical line test. And that means you are going to take a vertical line and pass it anywhere throughout the graph. Anywhere. And if your vertical line only hits one data point, then it is a function. So if I do a vertical line test here, one data point, one data point, one data point, one data point. But look at this last one. I'm going to change his color. Let's make him yellow. This one is not a function. So the reason is because your x values do not have unique y values. That is the mathematical reason. But if we were to use the vertical line test and I passed it right here, passed there and there, it can't hit more than one data point and be a function. If I pass it through there, hits there and there. This one is not a function. In the easiest terms, it's because it does not pass the vertical line test. All right, it's time for you to try. This is the bottom of page 173. I want you to draw a graph that represents a linear function. What equation represents the function? All right, linear's got to be a straight line. If it's a straight line, you can go ahead and write an equation in slope-intercept form. So go ahead and do that, and then come back for checking. Okay, here's mine. It's going to be different from yours. That's okay. But I just wanted to give you a flashback to how to write this equation. I'm going to pick this dot, and I'm going to pick this dot. So my slope is down 1 over 1. If I divide those, my slope is negative 1x plus, it crosses at the 1. And it's downhill, and I have a negative slope, so yay me. This lesson has been about how to represent functions in different ways. And we did bunches of them. So we did tables, we did graphs, we did an equation, we did a bar diagram. All right, so if you look at this, this is exactly the same information. It's just shown different ways. So here we have our table. So if you look, our rate of change is 2.5, and our starting point is 0. I know it's 0, or I'm sorry, our starting point is 10 because I look right there. So every time I'm adding a ticket, I am adding 250. Add a ticket, add 250. Add a ticket, add 250. That sounds suspiciously like y equals 2.5x plus 10. All right, second, you can absolutely graph that. So it looks like my starting point is 10, and I'm going to add 250 for every one ticket, 250 for every one ticket, until I have a linear graph. All right, you're going to notice that there is a squiggly line in between here. It didn't really show up on my slide, but that's okay. The first thing you learned about were the different representations. The second thing you learned about was that not every function is going to be linear. If you have any curvy swervies like this guy right here, he's not straight. He's still a function, but he's swervy, so he's non-linear. This guy right here, he is a linear function. All right, so you are on page 174. I want you to do the do you know, numbers 4 and 5, and I have left you an answer key so you can self-check.